Lab 1, charge tapes. In this experiment, we will find the charge of the tape through different amounts of testing. We will also compute the numerical charge Q in coulombs and the amount of electrons and atoms on the tape. We will also be using GlowScript to make a computational model. In this experiment, we will mainly use Newton's second law and use the Coulomb's law. First, we start off by finding the charge of the tape through different amount of testing. The first experiment, with our charge tape, we have the tape plus our hand, which attract, the tape on the tape, which repel because of the like charges, a tape in the book, which attract, and the tape in the pen, which also causes an attraction. This is due to the opposite charges, which will attract magnetically. We can conclude that the tape is positively charged from these small experiments. Now, for our main experiment, we will be finding the minimum distance to feel the electric force, and we will also be using Newton's second law and Coulomb's law to find the charge. Recall that Newton's second law states that our force is equal to the mass times the acceleration, and for our system, we will be stating that our total forces F net is equal to the magnitude of gravity plus the electric force, which is equal to 0, as when we make our point of contact, the objects should not be moving, which will cause no acceleration. Applying Newton's second law and the Coulomb's law. Here we have listed the electric force, which is 1 over 4 pi epsilon naught times q squared over the distance squared, and the magnitude of gravity, which is simply mass times acceleration g, which is 9.8 meters per second squared. Because in our last slide we stated that there is no acceleration and that our F net is equal to 0, we can state that our magnitude of the force of gravity is equal to the opposite of the magnitude of the electric force, which should have the same magnitude but opposite directions. Breaking this down, we can say that mg is equal to 1 over 4 pi epsilon naught times q squared over d squared. And we can find our charge q by simply isolating the variable, and we end with the square root of mass times acceleration times 4 pi epsilon naught times the distance squared. Now we'll be performing calculations. The length of our tape is 0.2 meters, and the mass is 0.0002 kilograms. The average distance to the force is 0.033 meters. Our first calculation is the force of gravity, which is mass times acceleration, which we get 1.96 e times 10 to the negative 3 newtons. And we use this to compute our Q, which is 1.54 times 10 to the negative 8 coulombs. Calculations continued. We can find the number of electrons on the tape by having our calculated charge divided by 1 electron charge, which will give us 9.6 times 10 to the 10th electrons. We can also find our number of atoms by dividing the area of the tape over the area of the atoms, which we get 4 times 10 to the 17th atoms. And we can find our ratio of electrons to atoms by dividing the number of electrons over the number of atoms, which we get 2.4 times 10 to the negative 7 electrons per atoms. Questions to think about. What if electrons had a positive charge and protons had a negative charge? What would change about the observations? Simply to put it, nothing would change. The interactions would remain the same. It's just that the charges are opposite from each other. So we will still have like charges and unlike charges, which will cause attraction or repelling. And it says, why is it important to handle the charged tapes as little as possible? What happens to the charged tapes when it comes into contact with your hands or other objects? Well, we found in our last experiment that our hands had an attraction from the positively charged tape, which states that our hands have more of a negative charge, which will influence the amount of electrons and protons inside of the tape once we make contact with it. Our GlowScript model. In this code, we essentially set the same conditions and do the same calculations just inside of Python. We have our initial conditions. We also calculate the forces, and we are able to create a visual model and find the amount of electrons on the tape and the charge. Here we have our model and the charge of the charge tape of B with the amount of charge on the tape and the amount of electrons. In this model, our blue arrow shows the electric force, which points opposite of the other charge tape because of the same signs, and our weight force, or mg, which is the purple arrow, that pulls down.